Okay, today we're going to continue on. We're going to pick up something that's actually defined in the chapter 0 of our book. So equivalence relation. We'll define them now. When you study math, you study about how things are equal to each other. So you have the notion of equality. The equivalence relation generalizes this. So again, the motivation behind this is given a group G and a subgroup H of G, does the number of elements in H, which we call the order of H, always divide the order of G? And it may be a couple of lectures before we get to answer this question, but that's the motivation behind this. We're kind of developing the structure to allow us to answer this question. So the first tool we need is an equivalence relation. So a definition equivalence relation is a subset or let's say it's on a set. So an equivalence relation on a set S is a subset of the Cartesian product, the set of ordered pairs S cross S with the following properties. Now let's give this equivalence relation a name. Let's call it R, the equivalence relation R. So it's a set of ordered pairs with what properties? Well, think about equality. What do we know about equality? Everything is equal to itself. So A comma A relates to A. So when you think about being in an equivalence relation, an ordered pair A comma B is an equivalence relation, means A relates B. One thing about equations, when you solve equations, it doesn't matter. You can switch sides. You can move everything from one side over to the other side and do the same to the other side. So that means anytime we have two elements in the set, if A relates B, that implies B relates A. And then one thing, you can substitute equality. So if you have three elements, if A equals B and B equals C, so if A and B is in R, and B and C is in R, that implies A comma C is in R. So again, just that's in the notes, and usually we write A twiddle, A relates B instead of A comma B is an element. So again, think of inequality, instead of saying 5 equals 5, what we really are saying is 5 comma 5 is an element of this relation equality. So that's an equivalence relation. And these have names, like a mirror reflects on itself. So we have reflexivity. Switching sides, that's symmetry. And this one is probably more familiar. I think it's covered maybe in some of the curriculum of transitivity. So we're going to get a key relationship right here, first of all. So we think about the S is the integers, all the integers, positive and negative. M is an integer, M is a positive integer. So a positive integer, and we say we define A is related to B if the difference A minus B is divisible by N. By N. And this is an equivalence relation. And again, I've got this worked out in the notes in some detail. So just quickly, if we look at why does A relate A? Well, if you look at A minus A is 0, which is divisible by N. So we have flexivity, we have symmetry. If A relates to B, then B minus A, then A minus B is divisible by M. So there exists an integer Z with A minus B equals T times M. So B minus A, that's just the opposite of A minus B. So if I multiply by -1, which using the associativity of multiplication is equal to negative T times M. So B minus A is divisible by N. So B relates A. So we've got the symmetry and transitivity. We assume A relates B and B relates A. So that'll give us two integers, S and T are integers. Again, we're reusing T. We've proved this thing here. So with, well, A minus B is T M, and B minus C is S times M. So what does that tell us? That tells us that A minus C, well, one of the math tricks is we add and subtract the same quantity, so add and subtract with B, but this is T times M plus S times M. And so A minus C is equal to an integer times M, so that means A relates C. So this is an equivalence relation. This equivalence relation is just called equivalence mod M. So each positive integer gives us a different equivalence relation. Okay, so we'll start talking about one of the useful things about the equivalents is once they help us break up a set. Take an element, look at everything equivalent to that element. Okay, that's some of the elements in the set. Maybe it's the whole set. If not, then take another element that's not an N and break up. So the equivalence relation helps break up a set, and we'll make that matter precise coming up. so given a set S and an equivalence relation twiddle or R we define for each A and S this following set. It's called the equivalence class determined by A. And it's just everything that's all the X elements, all the elements in the set S that are equivalent to A. So again, we use twiddle or tilde, just instead of writing A, comma B in R, or X, comma A in R, we write X relates to A. And this is called the equivalence class determined by A. When we're looking ahead, some of you may have seen the idea of a notion of a partition, a way to break up a set into disjoint pieces that have no overlap. And that's really what these equivalence classes will do. They will allow us to partition a set. So we have a couple of properties. First of all, note for all A and S, A is certainly equivalent to itself. That's the reflexivity. So if we look at the union over all the elements in S of all the equivalence classes, this is a union. This union will exactly equal the whole set. So as we'll see, we'll define a partition in a little bit. That's one of the properties of the partition. Also, what we have is given two elements in S, what can we say about the equivalence class? Well, either it's empty, their intersection is the empty, or the sets exactly coincide. So each piece is, the distinct pieces will be disjoint. So any two equivalence classes, they either have nothing in common or they're the same thing. The same. So let's try to show this. So we want to prove two statements, A or B. So what we can do is, let's assume if A equals B, the equivalence class determined by A is equal to the equivalence class determined by B. We're done. So the proof of this, all we have to do is assume that they're not equal. And then we need to show they're disjoint. So that's one way to prove, in general, the way to prove A or B. One way to prove that is you could assume not B and prove A. So that's what we're going to do after I erase the board. So let's assume these two equivalence classes are not. Notice we've already used, what property of the equivalence relation have we used? So far we've used the fact that the reflexivity guarantees that the union of all equivalence classes gives us the whole set. Now, these equivalence classes, there might be some overlap. There's not, and that's what we're trying to prove. So we'll probably have to make use of transitivity and/or symmetry. You think you probably would need both. So let's see what happens. And I will maybe work as formally as I did in the note. So if it's disjoint, X relates to A and X relates to B. So if X relates to A, that means X is equivalent to A, and if X is also in the equivalence class determined by B, X is determined by B. Okay, so how can we go about proving that? So that's just one thing to note here, and then also we have, so we'll probably make some use of that. Now let's try to show that these two sets are equal. So let Y be in A. So Y relates to A, but we also have, since X relates to A relates to X, here you're using symmetry. So by transitivity, if Y relates to A and A relates to X, Y relates to X. But if Y relates to X and X relates to B, by transitivity again, Y relates to B, so Y is an element in the equivalence class of B. So what have we shown? We have shown Y is any element. What's special about Y? Nothing. It's just any element in A. It has to be in the equivalence of B, in the equivalence class by B. So that equivalence, and the equivalence class determined by A is inside the equivalence class determined by B. And similarly, you can make an argument that B is contained in the equivalence class of A, right? If we took a Z that's in the equivalence class of B, well, Z would relate to B, but then this would also be the same as B relates to X, so Z would relate to X. But since X relates to A, that would mean Z relates to A. Also, in the notes, I actually gave a detailed proof for congruence mod M. I actually worked out a separate proof of that, did the specific case first, so you can read through that. But this covers that. Okay. So this applies when the equivalence relation is congruence mod M. Let's look a little bit more about in that special case as to how the partition works. So, how many distinct equivalence classes are there in this case? So what I claim is, again, given an integer a and z, there exists two integers in z by the division algorithm. If we divide by m with a equals qm plus r, where r is strictly less than m, in other words, since r is an integer, r has to be less than or equal to m minus 1. So what does that mean? So a minus r is divisible by m. So a is equivalent to, a is in R. So these two equivalence classes are non-empty. So they must be the same. So if we look at all the integers, each integer, the equivalence class determined by any integer, is in fact one of the equivalence classes between 0, the equivalence class determined by integers between 0 and n plus 1. And this R has to be unique. Why not? Why? Since if there's another equivalence class determined by an integer between 0 and 1, 0 and m minus 1, but that would mean that if that would mean a minus r prime is q prime m for some integer, so a would be q prime m plus r prime, where r is between 0 and m minus 1. And by the uniqueness of the division algorithm, we would have that r and r prime would have to equal. So again, if A is a set of all integers x such that it's equivalent to A, so such that A minus x is divisible by m, then Z is the equivalence class determined by 0, union of the equivalence class determined by 1, all the way up to the equivalence class determined by m minus 1. Where, say, the equivalence class are not equal if if we take any two distinct one of these, if the two integers are not equal, then their equivalence classes are not equal. And so we denote, this is some notation we'll get back to quite a bit, Z sub m, the integers mod m for the equivalence classes of Z under congruence mod m. So we also have a definition. We can generalize this idea for any equivalence relation that we've already actually proved for the equivalence relation, the idea that they partition. So this would be a way to partition Z, in this case, into m different subsets, each of which, any two of which have nothing in common. So we define a partition P of a set S to be a collection of subsets PI, where PI is, each PI is a subset of F. Say a collection P sub I is in some capital I. Capital I is just like an index set. So usually capital I can be like 1, 2, 3, just a way of labeling them. So each element of the partition is a subset of the set X. If we union over all of the index sets, so we take all these subsets and union them together, that gives us the whole set. And if I is not equal to j, then either Pi equals Pj or Pi intersect Pj is equal to the empty set. So that's a partition. So really what the integers mod n, that's a way of partitioning the integers mod m, is a way of partitioning the integers into m disjoint equivalence classes. it turns out an equivalence relation gives us a partition, and all partitions give us an equivalence relation. So the equivalence classes of an equivalence relation form a partition of the set S. Of an equivalence relation on S. So theorem the equivalence classes of an equivalence relation on S form a partition of the set S. Conversely, every partition determines an equivalence relation. Every partition of S determines an equivalence relation on S. Okay, given an equivalence relation twiddle where the equivalence class is just everything that's equivalent to A. Today, on this lecture, we have already shown that first of all, if we union over all A and S, we would get the entire set S, and either two equivalence classes are equal, or their intersection is disjoint. That's exactly the definition of a partition. If we just look at all the equivalence classes of A, as we let A go over all elements of S, we get a partition. What about the other implication? And before I go through that, I just wanted to make a remark. I probably should have made it earlier. This idea of a relation, remember how it was initially defined, it was a subset of the product S cross S. And sometimes you actually see that in a function definition, right? If you have a function as a collection of ordered pairs, you may have seen when they define a function, they first define a relation as just a set of ordered pairs, and then a function is a special type of relation such that, each element, each ordered pair, for each element in the first component of the ordered pair, there is exactly one element in the second component. So that's a special type of relation. So that's one special type of relation is a function. If you think of a relation as being a product of S cross S, S with itself. And same thing with an equivalence relation is another special type of relation. What about the opposite implication? Now we want to prove each partition determines an equivalence relation. So let P consistent of these PI's, where I goes through some index set, be a partition. So the PI's are just the elements of the partition. Okay, what I claim is let's define let xy be in S. We define x is related to y if there exists an I in the index set with x and pi and y is also in that same index set. So that's how you get an equivalence. A partition breaks up the set into these different block subsets, and we'll say two elements are going to be equivalent if they are in the same block of the partition. So that's certainly a relation. Is this an equivalence relation? We want to verify the three properties. Reflexivity, symmetry, and transitivity. I can't say transitivity. Yeah, I guess maybe I can. So the symmetric, well, since by definition of a partition, S is a union of this overall set. There exists an I and I with X and PI. Here maybe I can change it J. So I probably shouldn't use I twice. So here my J is a so-called dummy variable. I'm just using J to index over all of them. So J, I run through all of these index sets. One of these various J's has to contain X. So let's call that J and I, whatever that specific one is, let's call it I. So there's some I as an index with X is in PI. And so if X is in PI, then X is also in PI. And by definition of our equivalence relation, that's enough to show that it's equivalent. So that's reflexivity. Again, all the partition, the sets partition the whole set S. An element X is in S So it's got to be in one of those partitions called PI. And so X is in PI and X is in PI. That's exactly the definition we use. 2. Let's show symmetry. Assume X is in PJ, or X is equivalent to Y. We need to show Y is equivalent to X. Well, let's look at it. Since X is equivalent to Y, there exists some index set, there's some I in the index set I with X is an element of PI and Y is an element of PI. Well, certainly, with the English language, A and B and A are the same thing. That's really the same thing as X is equal in PI and, Y is in PI and X is also in PI. And so that's exactly where the symmetry property holds. So we've shown that if X is equivalent to Y, if X and Y, if X is in the same, really what this is in words, it's really saying X and Y, X is equivalent to Y if X is in the same block as Y. Block, I guess that's what I'm calling these PJs, the same subset of the partition. So if X is in the same partition as Y, same subset of the partition as Y, then Y is in the same subset of the partition as X. Okay, let's now show symmetry. So that's symmetry. What about transitivity? So we assume X relates B and B relates C. We want to prove that A relates B and B relates C. We want to prove that A relates B. So let's see what we can do here. What does that mean? So there exists an I in I such that X is in PI and B is in PI. There exists another index J in I such that B, this is because A relates B. B relates C, so B has to be in PJ, and C has to be in PJ. But what does that tell us? That tells us that B is in the intersection of PI and PJ. So there's something in that intersection. It's not the empty set, that intersection. So by the nature of a partition, if you take any two of these subsets of the partition, which I sometimes call the blocks of the partition, if those two have, if any two of them have something in common, they have to be the same. By definition of a partition. So C, not only is it in PI, not only is C in PJ, but C is also in PI. PI is PJ. So A is in PI, C is in Pj, which is Pi, so C is in Pi, therefore A is equivalent to C. So we've got an equivalence relation. So each partition determines an equivalence relation, and we've already proved that any equivalence relation will lead to a partition where the blocks of the subsets of the partition are just the equivalence classes. Okay, so we'll stop here for a moment, and then we'll look at a special type of equivalence relation in groups. Maybe before I do, let's just maybe close with an example. I think if I ever get around to doing some online short quizzes, this would kind of be just a true or false question. Let S be the set of all lines in the plane. And we define L1 equivalent to, or L and M are lines. L is related to M if L and M are parallel. You can think about, is this an equivalence relation? It's actually not an equivalence relation. Why? Well, if L is parallel to M, and M is parallel to L, M is parallel to another line M, then they would be parallel. Then we would have that. So you sort of have the transitivity. If one line is parallel to a second line is parallel to a third line, the third line should be, and the first line are parallel. And certainly if L is parallel to M, M is parallel to L, so we've got that. But it actually fails for reflexivity, right? I would not say L is not parallel to itself. Sometimes those are called, I think, concurrent lines. So that would not be an equivalence relation. I think you can modify it as an equivalence relation. You could say L and M L is equivalent to M if they have the same slope. So that's an interesting just example. Again, idea definitely right from the high school geometry curriculum, parallel lines. And initially, when I first wanted to get this as an example, I said, oh, this should be a good example of the equivalence relation. But I forgot if it's not a distinct line, L is not parallel to itself. So we'll stop here for a moment.